Oh, wow. Okay. So I'm much shorter than everybody else, so I'll step to the side here. Otherwise, you'll be staring at the back of a monitor. Hi, everybody. My name is Ty. I'm from AWS, and I've been asked to give the third workflow example here. And as a team, we thought that the generative quantum eigensolver would be a good one to stimulate some discussion about how difficult or the challenges that we see when trying to implement some of these hybrid workflows going forward, and maybe areas that we can work together. Just a reminder, right? This is an interactive discussion, and we put up 3 what we consider maybe provocative statements at the beginning of this session. And the reason for that is just, do you agree or disagree with this in the context of the workflow that we're going to be talking about? And just to remember, right, no hybrid workflows we know today actually need HPC. Agree or disagree in the context of the application or in general? Right? No end user application requires tight integration. And the third one is for quantum classical systems, tight integration does not require co-location. Now, again, let's see. I'm not going to form an opinion on this one, right? I'm going to set the stage, put out a workflow, and then throw it all to you to stand up and let us know what you think. Okay, so as you've seen through the other talks and probably throughout the week, there are a set of common workflows that we see, or hybrid workflows, right? We see iterative workloads where we're hopping back and forth between the quantum and classical processes. We see pre-processing, post-processing, and then situations where we need both pre and post-processing. And today for GQE, it falls under the iterative type of workload. Now, normally when we discuss the challenges associated with hybrid workflows and scheduling for iterative type workflows, we oftentimes have a picture like this in our mind, where it goes back and forth, and really the only challenge that we have is, does the classical compute take a long time, or does the quantum compute take a long time, and what happens when the wall clock time or resources necessary for those swap. I'd like to build on that with GQE because I think it's an interesting workflow that takes this and then kind of expands the complexity or the challenges that we'll see through this iterative process. I'm a chemist, so I thought I'd introduce it in the context of chemistry. It was also presented this way in its first publication with the University of Toronto and NVIDIA, I believe, right? So keep me honest here. So at its base level, quantum chemistry, at least electronic structure theory, is interested in calculating ground state energies for the most part. And one big challenge we have is that, here's an example of the hydrogen molecule. We have a fixed distance between the 2 atoms, and we calculate the energy of the system. And then what we do is we start to move that distance. And if you scan across that distance, you get something here called the potential energy surface. Now, what happens is it's classically not too hard to calculate the energies when we're near an equilibrium distance, when the bonds are fairly robust. But as we start to stretch it apart and break those bonds, that's really where classically we need some expensive approaches available to us. And so a lot of the work that's been motivated in the area of quantum chemistry and the field of quantum computation is, does quantum computing provide a way for us to more efficiently calculate that part of the potential energy surface? All right, so how do we do this? Well, what we normally do is think about electronic configurations. And so what I mean by that is we need a way to generate approximate wave functions in such a way that it makes sense that we're able to create truncations or approximations in a systematic fashion. And so what we do here is you can think of electrons in the system and the orbitals. And we can take the electrons and, in its ground state or stable state, we have in the hydrogen molecule 2 electrons in the lowest energy orbital. And we can start to create configurations that we can then use to describe our space by adding single excitation. So we take that electron and we move it to different orbitals. We can then go forward and create configurations where we move 2 electrons at a time. And the way that we construct our approximate wave functions is by taking linear combinations of these configurations. The hydrogen molecule only has 2 electrons, so we're stuck at double excitations. That's as far as we can go. But you could envision systems with more electrons and having a greater number or higher degree excitations. And a lot of the approximations that we make are based on the truncation of that excitation level. Okay, so why is this important? This is important because that's kind of the underlying foundation for unitary coupled cluster singles and doubles. That's been very popular with variational algorithms like VQE. So what we do here on the top left, and I'm sorry that I didn't have the time to bring them in, is on the left-hand side, do I have a pointer? Was there a laser pointer? Try not to take anyone's eyeball out while I do this. It's on. Where's the? Oh, okay, here we go. Now move this way as well. So up here, this is our ansatz, right? This is our approximate wave function that we're going to create this state on the quantum computer, and you can see that it's parameterized. And what we've done is we've broken those T's into singles and doubles. And those are the configurations that we have. It's just the way that we implement them for unitary coupled clusters. That's just an ansatz, an approximation that we've made. And so we have a linear combination of singles. Again, the parameter here, you can see that there's an annihilation and creation operator. Right? So that's us moving the electrons into different orbitals. And we also have the set of doubles as well. And then in VQE, what we do is we evaluate the expectation value. So we get the ground state energy. And then we update the parameters on the classical computer. We go back and forth. This has stimulated a lot of very interesting work. But one question that the authors of the GQE paper posed is, well, what if we can take advantage of a lot of the machine learning capabilities and tooling that we have today to take the parameter optimization on a classical computer and put it into that type of framework? What do I mean by that? The idea is that the GQE algorithm optimizes a classical generative model that produces circuits from a pool of operators. And in this case, what we're going to do is we're going to say, okay, let's take the excitation operators. There's a pool of excitation operators, right? And let's take some combination of them and see if those lead to the expected outcome that we want, which is a low ground state energy. So again, side by side, classically here, this is what we do. Everything's in there. And then on the GQE side here, what happens is these are now proposed by a generative model. And as we start to update and train the model, we can take advantage of all the machine learning tooling that is available to us and has been invested in heavily over the years. Okay, so this is a very simple slide on how this kind of works, and then we'll just jump into the workflow and I'll throw it out to the floor. What we do is we take our set of singles and doubles here, right? So they're linear combinations, but you take every element within this expression, and we don't know the values of the parameters. So in addition to the pool of these, we discretize the parameters. And we say, okay, so you have one excitation with a parameter, and let's say we discretize this parameter to 11 points, right? We now have 11 of those, and we do that for every sum. And that creates our singles pool and our doubles pool here. That is used to train our model. And then eventually, when we have a trained model, we hope that what it does is suggest an ansatz for us from this operator pool that works very well to return a reasonable energy. Okay, so I'm not going to debate the quality of the energy or all that other stuff, but this is a very interesting application from a workflow perspective. And the reason for that is this is kind of what it looks like. And I'll walk us through this slowly. What we start with is kind of a pre-training and then a training section. And in our pre-training section, what we do is we calculate our Hamiltonian, or the elements of the Hamiltonian that we need. And that's done on a classical resource. Let's call it classical resource A. From there, we need to generate an initial set of training data. And those are circuits. And we can evaluate those circuits either on a QPU or a simulator. And because there are a large number of them, you can envision this being an embarrassingly parallel step to a certain degree, right? So if you're on a simulator and the circuit is small enough to fit on a single node, then all you're doing is spanning over those, calculating them, pooling them up. You could envision a scenario where the circuits are so large that you need an HPC resource for the X to evaluate each of these circuits. And then again, you're doing that in parallel, right? And the resources that you use, be it quantum or classical, may be very different from the resource that you needed to evaluate the Hamiltonian. And so now we're changing to a different type of compute resource. And then from there, we move over to the initial setup of our model. And that oftentimes tends to be a tightly coupled set of nodes with GPU acceleration or some sort of accelerator attached to it. Then we move through the iterative process, right? That's when we start training. What we do is we say, okay, well, we've warmed up our model. Let's go ahead and have it propose a set of ansatz. Let us take those circuits, evaluate them, and then update our model, and then we iterate to convergence. So I see a number of challenges here for us, right? Not only are the types of resources changing, these could either be quantum computers or these could be classical simulators. We also have to calculate the Hamiltonian elements. We're training our model. We have to perform some sort of inference for it to suggest the next set in this iterative process. And these can take a long time. So one real challenge we face is you, at scale, have to stand up an enormous number of classical and quantum resources, and then they sit and wait for a while. That's like the worst case scenario, right? And okay, so that's the setup. And I'm going to kind of throw it out because this is supposed to be a community discussion. I'm curious. My question to everybody is, well, does this seem like a problem to you? How would you do it? Are you not concerned at all? Is this aligned to something that you're working on? Let me know.
Yeah, working in emerging technologies doesn't help with microphone. So no, I mean, a problem that the first thing that I would think is how do you schedule this, right? So the very first slide that you show, so classical, quantum, and all the blocks. So I immediately thought about, how do I request the QPU here? Shall I just leave an open request and let the QPU allocate it to me for X many hours, or I allocate it and then deallocate and then back and forth, back and forth, back and forth. So I don't know. This is something resource-wise is going to be a problem if not taught properly. I don't know. Sounds boring, maybe, but yeah.
So the way this is depicted, there is a phase. I mean, just going from left to right. Okay, we're starting a classical domain. We have a series of quantum computations that happen. And then schematically, this is all reducing to a single line. Okay, so is that in fact necessarily a barrier that we have to implement there? In other words, do all of the quantum computes have to complete before any of the first phase of classical parallel compute starts?
Yeah, it's a good question. In the training, I think that it has been proposed, or it is possible to kind of load balance them, meaning you could do smaller batches of trials and update your model with a smaller number. And so there may be an opportunity to keep this resource busy while this resource is also working. The question is whether or not, based on the quantum computers are limited resource, and so are sometimes classical resources.
No, my question is really for example, I mean, pre-training or training, and they may be quite different, but and if they are different, please explain.
Talking about this line.
Yes. Okay. Yeah, I'm talking all along that line there. So what I'm really asking is, does, for example, the line of blue classical compute boxes, do all of those classical quantum computations have to have completed before any of the following classical phase can begin? In other words, do they really require the data aggregated from all of them before any of them can move forward, or is there in fact some fragmentation of things that would allow a more flexible initiation? Because I mean, if you put a barrier, that tends to create idle resources.
Yes, I think in its base implementation, the model training happens on a batch of output. Mm-hmm. And so yes, in that case, the execution of the circuits and the energy would have to we'd have to have them all.
Okay.
But I'm not an expert in this algorithm, and just kind of basing it off of its initial implementation.
Again, it just has to do with how we construct the
But it's
constraints
a
and
good
the
question.
scheduler that we feed the workflow.
Yeah, it's a good question, right? You could envision another algorithm or implementation that would allow you that, and we would have to account for that type of scheduling and resource management. And I don't think we have a good way of doing that. Yes.
So maybe the similar question, do you expect any resource inefficiencies might happen, because of, this synchronization or barrier you have to put it in between? So I think earlier diagrams you showed whenever you're running quantum resources, classical resource may not run. Of course, it's a solution, how to, depending on how you implement it, but I think, do you expect any of the resource inefficiencies happen? Of course, quantum systems are very expensive, right? You want to make it 100%, running all the time, right? So,
yeah, I think this is that is indeed going to be a challenge, right? And I think this is more of a challenge for user facilities than it is for the user, right? Because for them, people will likely start running workloads that look like this, maybe, and given that they are a limited resource, do you impose policies that require them to release them? And how do you do that if someone's just running with it, right? I guess they're burning time or their allocation on those devices. But yes, there's a big chance that they'll sit idle, especially when it comes to the classical resources for the model training. If it takes a long time to execute your circuits on, let's say, a QPU, it makes a lot of sense to shut down the classical HPC resources doing the model training. And then you also have to wait for that thing to stand up again, right? So it could take a long time to evaluate these.
let's see. All right, thanks.
But then it also adds a lot of parallelization, right? Like when we are thinking specifically in terms of data that we are getting from the QPU side, and then again following the same machine learning flow basically. So there are opportunities to parallelize a lot of tasks here, which is good for CPU and GPU both on the HPC side.
Yes, yeah, we can absolutely play the game of wall clock time versus cost here, right? Whether or not depending on whether or not it fits on the resource, but yeah, you could absolutely optimize for time to solution and parallelize classically, yes. I think the note too is it's somewhere around, I think their first implementation, 200 to 1500 iterations based on the system that they were looking at. So it's quite a few iterations here.
Can I?
Yeah, of course.
So do you have a sense of how much classical compute is needed in the pre-training and training? And do you expect it to vary across, let's say, the kind of Hamiltonian and the kind of electronic structure Hamiltonian that you're trying to approximate, right? I can imagine if it's some simple diatomic molecule, the amount of classical compute is like, okay, maybe a few GPUs suffice. But then if you really scale the system up, maybe you need really non-trivial training and pre-training. And so for me, I'm always going back to the flexibility argument, which is that are we able to flexibly allocate resources based on the application? That's that. Yeah. So that's the context.
Yeah. Okay. So in terms of scale, you're absolutely right that the system drives everything, right? And so, for example, the blue boxes here, if we assume that they're simulators, if the system is small, we probably can use CPUs, not even GPUs. But if it grows, then yes, they become very expensive, very, very fast. And then for the machine learning model, and I believe that it's about 1,000 or so circuits that you'll want to have in a batch. So that's quite a few.
Yeah.
Right.
Yeah.
And then for the machine learning model, I think it depends on the complexity of the model. Yeah, but it will be tough because with the popularity of machine learning, especially at least I can only speak for the cloud, right? there's a lot of demand for these GPU accelerated resources. And so that makes it hard to schedule something that large, to train just one instance of the model and shut it down. And I don't think that happens classically, right? Oftentimes you can keep those resources busy. A little better than this.
One following up on that, do you see room here for adaptive algorithms? Because is it fair to say that these things can take their sweet time, more or less?
I'm sorry, the door closed. I wasn't able to hear
Sorry, I'm saying, do you see room here for adaptive algorithms in the sense that, let's say you do some pre-training and you realize, oh, I should be measuring this pool of operators instead? And or do you think that, oh, it really is, it has to go through the training and then only can you iterate on future choice of operators?
So the pool of operators is fixed.
Okay. It's the parameters, the thetas that you need to pick. So
Yeah, we discretize. I think that what they do is they discretize them,
yes.
right? And so how fine you want that to be, I think, is something that I don't know. I'm sure there's a trial and error thing,
Yes.
and that the people who have implemented this have a good handle on that, I would suspect.
Right.
Well, the other one to note is how long is your ansatz? Because you're no longer including the entire one,
Mhm,
right? How many of these base unitaries are you including in the expression?
Yeah, I just had a quick question. I think it might have been partly just answered, but when you say the number of operators is fixed, how does that grow with, say, with the size of the system you're looking at? Like in the standard variational approaches for chemistry, the problem is that you just have too many. The number of operators you have grows too quickly, basically. So these things are not scalable. Is that the case here?
Yes. So, okay, I don't know whether or not it's not scalable, but you're absolutely right. There's two things that drive the number of excitations you have. One is system size, and the other one is the basis set that you use, because that determines the number of virtual orbitals you have within your system. You can address that by creating an active space, but you lose a lot of the dynamical correlation corrections that you get, and so then you suffer on accuracy. So the size of the operator pool here, the number of single and double excitations will be driven by two things. Well, three, let's say three. One is the system size, absolutely. Two is the basis set that you select, and three would be how you discretize the parameter. And all of those would factor into the size of the pool. And I could envision that gets big.
Okay.
Especially if you're using real basis sets.
Got it. Thanks.
If you actually use the quantum computer to acquire the data, for the Fermi operators, you also need to do the transform. So have you considered just to use the qubit operators pool?
I have not. I have not implemented this algorithm. The reason I left it here as the Fermi creation and annihilation operators is just it's simple because we have short implementation, short amount of time for the presentation. But when they implement it, yes, they do a transform.
Yeah, but I have the question because the evolution of the adaptive VQE, latest edition they use the qubit adaptive VQE.
Yes,
in that way, the operator is more hardware efficient, so you bypass the like Jordan-Wigner transform, those sorts of things.
Yeah, I'm sure that there are a number of optimizations you could make to the algorithm and the implementation that would make things more efficient.
Okay, thank you.
The real concern, at least on my end here, is how you would manage these resources throughout the execution of the workflow, the training process. But you're right, finding little efficiency gains here and there makes a lot of sense.
If I might follow up a little bit, if we look at your pipeline schema, which sort of has the alternating phases, and as you pointed out, the pre-training quantum compute may take a significant amount of time. Various of these things may take long periods of time, and you said you might want to stand down the classical resources. In principle, is it knowable how long that phase is going to last, that you're going to be asking them to stand down. What does that depend on? Is it depend on the input data, or is it something that can be, estimated with a higher reliability?
Yeah, I think for the blue section, it is the number of circuits that you need to evaluate,
Mm-hmm.
and then the size of them. So I would imagine you could get a good estimate on that. You could run it once, right, and say, okay, ballpark, the executing one circuit on a simulator or a QPU takes this amount of time, and then from there it's just scaling up by the number that you need and the resources available to you. The model training, I'm not entirely sure, right? I would envision that you could get a ballpark based on the number of parameters that you are adjusting.
Yeah.
As part of the process, the training process.
Yeah, I mean, this is one of the things that maddens, just about everybody doing these hybrid pipelines, is that you've got these phases that take so long. And
Yes.
if you're dealing with traditional HPC scheduling techniques, then, okay, I've got all my resources, I launch them all at once. And typically it's because they're all going to be active at the same time.
Mhm.
And you break these things into phases where things, need to be stood down or sitting there idle and being paid for. It makes people slightly crazy. At some point, I think we're going to have some kind of schedule-based, time-based, predicted time-based scheduling on these things. And I'm just getting some feel for the volume of applications where that can even be applied.
Yeah,
Okay,
I think
thank
it
you.
is becoming increasingly clear that we need a lot of information from the quantum systems if we're looking at hybrid scheduling. Question is, what are the ones that are really going to move the needle for us to allow us to start to build these and test them?
Yeah, you're more optimistic maybe than what we're going to discover the truth to be. We've been trying to do this in the HPC community for how many years?
A long time, and it's wildly imperfect, but I'd like to think we can at least ride on what knowledge we've acquired.
Well, yeah, I'm not sure we've made a lot of progress. I mean, I've seen studies or at least read papers even in the last couple of years. Maybe it's been a couple of years since people have been looking at this, since all papers are AI nowadays. But yeah, but even if you go back 3 or 4 years, where people were studying, the Qs and finding that, all of the different predictions were, mispredicting a fair percentage of the time. In classical HPC, while it would have been nice to hit it more accurately with the ability to do checkpointing, if you're off by a little bit, there was a fair bit of amelioration here. I think this is introducing another challenge to the scheduling aspect, right? Because either the resources are sitting around idle, or you're having to spin them down and then restart them, which also there's a meaningful cost to. So it is definitely introducing, I think, an additional parameter or dimension to the scheduling.
And feeds into this whole notion of we need to understand what we mean by loosely versus tightly coupled. And so.
Yeah, somebody said it earlier. I mean, I agree with you. We should definitely come up with a definition. Tightly coupled to me seems to be milliseconds less than milliseconds, right? I mean, something where you want to have them. I don't know about the co-location. I mean, we can talk about co-location in terms of tight coupling, but where you would want to be able to first of all have them having a consistent scheduling across them. Right, so that you're not standing them down, but where you need a more of a high performance network, right? If you're just going to have Ethernet or the internet or pigeons or whatever carrying them, then that's not tightly coupled. And that's probably, in the order of 1 to 10 milliseconds or less than. But that's just my take. Everybody, of course, can weigh in on what they mean by tightly coupled. Yeah.
To add to that co-location point, I think it's also about data governance. Like if we are looking at what workflow we are running, what data we have to keep, using for within our HPC systems, right? So we have to look at that perspective also. Yeah.
What if you use perturbative triplets in the classical training to help the quantum circuits get to the correct energy? Like, does it break the whole system, or would it actually help you get to? And then do some learning from the triplet.
So I'm not sure that that would help all that much. You could always tack it on at the end, right? But what the model is trying to learn is if I pick these elements from the pool, will I get a lower energy? So it's the action of the impact of those elements that it is selecting from the pool that it is trying to understand. That's my guess. I don't know, could be wrong. Just yeah, I did see Amir kind of poke at me and say they're eating outside. So
Awesome. So that schedule worked out almost magically.
yeah.
So if there are no more questions, then I think we can go for lunch. So thank you, Tyler. Thanks all the speakers.
Thanks, everybody.
Thanks for